Right now, a new image of one of the brightest, strangest stars in the entire night sky is spreading across the internet, and almost everyone sharing it is getting one crucial detail wrong. No star this close to Earth has ever kept a secret this well for this long. No observatory has ever managed to catch what this new image just caught. It is not a photograph from the James Webb Space Telescope. It is something arguably harder to get from an instrument almost nobody talks about. And what it just confirmed rewrites part of what we thought we knew about the star everyone calls Betelgeuse. Stay with me, because the real story is stranger than the headline. If you're new here, this channel breaks down real space discoveries the moment the data lands. No filler, no science fiction. So if that sounds like your thing, hit subscribe. It costs nothing. Let us go back to the beginning. Betelgeuse sits on the shoulder of Orion, one of the easiest stars in the sky to find with the naked eye, glowing a distinct burnt orange among the blue-white stars around it. It is a red supergiant, a star so enormous that if you swapped it in for our sun, its outer surface would swallow Mercury, Venus, Earth, and Mars whole and reach nearly all the way to Jupiter's orbit. That size comes from where Betelgeuse sits in its own life cycle. It has already burned through the hydrogen fuel that powers ordinary stars for billions of years, ballooned outward as it began fusing heavier elements, and is now living on borrowed time, cosmically speaking, somewhere in its final few tens of thousands of years before it ends its life as a supernova. Astronomers have known this for a long time, and none of it on its own is controversial. What has been genuinely difficult is measuring Betelgeuse precisely, because the very thing that makes it fascinating also makes it hard to pin down. It physically pulsates, swelling and shrinking on a cycle of a little over a year, which distorts the standard technique astronomers use to measure stellar distance. That's why you'll see the distance to Betelgeuse quoted differently depending on the source. Most recent estimates converge somewhere around 550 light years, though older figures ran meaningfully higher. Read that again. Astronomers can measure galaxies billions of light years away with real precision, and they still argue about the exact distance to one of the brightest stars in our own sky. None of this uncertainty reflects badly on the astronomers involved. Betelgeuse has been catalogued and watched for thousands of years. Ancient Chinese, Babylonian, and Greek skywatchers all recorded it, and its distinctive orange-red color has been described in written records for at least 2 millennia. Modern variable star observers have tracked its brightness continuously since the late 1800s, building one of the longest unbroken photometric records of any single star in the sky. That long baseline is exactly why the strange rhythms buried in its light curve stood out in the first place. You cannot spot a pattern that repeats every 6 years unless somebody has actually been watching carefully for well over a century. The standard model of a red supergiant's life is not in dispute here either. Massive stars like Betelgeuse burn through their hydrogen far faster than smaller stars like our sun, and once that fuel runs low, the core contracts while the outer layers swell dramatically, cooling to the reddish glow that gives red supergiants their name and color. That basic physics has held up under a century of scrutiny, refined but not overturned by 100 years of increasingly precise observation. What has never fully held up, until now, is a clean explanation for one particular wrinkle in Betelgeuse's behavior. On top of the pulsation, Betelgeuse has another long-term rhythm that nobody has fully explained for more than a century. Layered on top of its normal, roughly 400-day brightness cycle, there's a second, much longer variation. A rise and fall in brightness that repeats on a period of about 200 days or nearly 6 years. Astronomers call it the long secondary period, and it has shown up in Betelgeuse's brightness records stretching back over 100 years, and for decades, one leading explanation kept surfacing in the scientific literature. An unseen companion star orbiting close enough to Betelgeuse to periodically disturb its light, but too close and too faint to actually see. It was a completely reasonable hypothesis. The timing fit, the mathematics fit. But reasonable is not the same as proven, and proving it meant doing something that sounded almost absurd. Astronomers would need to directly photograph a companion sitting practically inside the glare of one of the brightest stars in the sky. That's the number to hold on to for the rest of this story. 2,100 days, repeating for over a century with no confirmed cause. Then, in late 2019, something happened that had nothing to do with any hidden companion, and it briefly convinced part of the world that Betelgeuse might be about to explode. Over a matter of weeks, the star's brightness collapsed. Betelgeuse normally sits around magnitude 0.5, one of the 10 brightest stars visible from Earth. By February 2020, it had dropped to roughly magnitude 1.6, a loss of about 2/3 of its normal visible brightness, an amount of dimming, large enough that casual observers noticed it with their own eyes, no telescope required. Here's where it gets worse before it gets better. Betelgeuse is close enough and massive enough that when it finally does go supernova, some astronomers estimate it could briefly appear, roughly as bright as the full moon in Earth's sky, visible even in broad daylight for weeks. So when the star that's supposed to do that suddenly started fading in real time, the questions writing themselves in astronomy departments and social media alike were obvious. Is this it? Is Betelgeuse dying right now? It wasn't. In 2021, a team led by astronomer Miguel Montargis published the answer in the journal Nature, built on images captured by the European Southern Observatory's Very Large Telescope in Chile. Comparing images from before and during the dimming event, the team found that part of Betelgeuse's southern hemisphere had visibly darkened, as if something had been dropped in front of it. What actually happened, they showed, was that the star had thrown off a massive bubble of hot gas from its own surface, and shortly afterward, a patch of that expelled material cooled enough for heavier elements inside it to condense into solid dust, essentially forming stardust in real time, directly in our line of sight. Betelgeuse hadn't started dying. It had, in effect, briefly put on sunglasses of its own making, and taken them off again once the dust cloud drifted clear. Sit with that for a second. The star wasn't collapsing, it was smoking, in the most literal sense the word allows. The episode still mattered, even with the supernova panic put to rest. It was the first time astronomers had ever watched a star's own surface visibly change in near real time, week to week, using direct imaging rather than inference from brightness curves alone. A genuinely new way of studying how the largest stars in the galaxy lose mass as they age. Researchers studying the data were clear afterward that the Great Dimming wasn't some freak one-off event either. It was an unusually large version of something red supergiants likely do routinely throughout their late lives, shedding material into space in fits and starts as they burn through their final chapters. That shed material is, on long enough timescales, part of what eventually seeds the next generation of stars and planets, a detail that makes the star was smoking description a little more than a turn of phrase. Here is where this stops being an abstract stellar physics curiosity and starts being personal. Betelgeuse is close enough, and its eventual death bright enough, that when it finally does explode, it will be one of the most significant naked-eye events in recorded human history, visible without a telescope from every populated continent on Earth, studied by more instruments in more countries than almost any astronomical event before it. There is no danger to Earth in that explosion. Betelgeuse sits far too many light years away to pose any physical threat when it goes, but there is something quietly humbling in the fact that a star most people can point to in the sky tonight, on the shoulder of one of the most recognizable constellations in the world, is already living, through the final chapter of its life, and has been for longer than human civilization has kept written records. Every culture that has ever looked up at Orion has been looking, without knowing it, at a star already on borrowed time. And every one of us alive right now has some non-zero chance of being around to witness the exact moment that borrowed time runs out. Nobody can predict which decade, let alone which year, but unlike almost every other astronomical event described as imminent in a headline, this one genuinely could happen within a human lifetime. And that combination of certainty about the eventual outcome and total uncertainty about the timing is rare enough in astronomy to be worth pausing on. For over a century then, astronomers had a mystery, the 200-day rhythm, and a leading suspect, a hidden companion star that nobody could actually catch. And trying to catch it turned into one of the more frustrating chases in modern observational astronomy. Astronomers had, in a real sense, a suspect, a motive, and 100 years of circumstantial evidence, and no way to put the suspect in the frame. The core problem was contrast. Betelgeuse is one of the most luminous stars visible from Earth, radiating so much light that any hypothetical companion star orbiting close to it would be almost completely drowned out, like trying to photograph a match flame held directly in front of a lighthouse beam. Standard imaging simply couldn't do it. Point a normal telescope at Betelgeuse, and any faint companion vanishes entirely into the glare of the primary star's light, scattered further by the telescope's own optics and by turbulence in Earth's atmosphere. Astronomers tried anyway, repeatedly across decades. Speckle imaging techniques designed to freeze out atmospheric blurring came up empty. Early adaptive optics attempts, using deformable mirrors to correct for atmospheric distortion in real time, still couldn't suppress Betelgeuse's overwhelming glare enough to reveal anything hiding close beside it. Each failed attempt didn't disprove the companion hypothesis, the 200-day. Signal and the brightness data kept showing up, stubbornly, on schedule, decade after decade. It just meant the tools of the moment weren't good enough yet. Some researchers, tired of the repeated null results, floated other explanations entirely. Convective cells the size of continents rolling across Betelgeuse's surface, or the star's own pulsation somehow producing a longer, secondary rhythm on top of its main cycle. Neither alternative explained the data cleanly either. The companion hypothesis kept surviving every attempt to kill it, and kept surviving every attempt to confirm it too, which is about as frustrating a place as a scientific question can sit for 100 years. Think about what that means. For most of the 20th century and well into the 21st, scientists had strong indirect evidence pointing at something they could not directly see, sitting right next to one of the most studied stars in the sky, hiding in plain sight because the sheer brightness of its neighbor made it functionally invisible. The breakthrough finally came by combining two specific technologies rather than relying on either alone. Extreme adaptive optics, which corrects for atmospheric distortion far more aggressively than earlier systems, paired with a coronagraph, a device that physically blocks out the blinding light of the central star so that anything faint sitting nearby has a chance to show up. The instrument carrying both of those capabilities is called SPHERE, mounted on the European Southern Observatory's Very Large Telescope. The same telescope, and in some cases the very same team, that had already solved the Great Dimming Mystery years earlier. Montargis and his colleagues pointed SPHERE at Betelgeuse again, this time hunting specifically for the companion the brightness data had been hinting at for 100 years, and applied every trick the instrument had to suppress the star's overwhelming glare. And this time, sitting exactly where the orbital math predicted it should be, something faint appeared in the frame that had never been there in any previous image. Here's the reveal nobody was fully braced for, after 100 years of looking. It worked. Here is what is happening right now in 2026. That image, released within the last several weeks and published in the journal Astronomy and Astrophysics, is being described by the research team as the clearest picture ever obtained of what is very likely Betelgeuse's long-suspected companion, informally nicknamed Betelgeuse B. According to the paper, Montargis and his colleagues state plainly that Betelgeuse is not a single star after all, but is accompanied by a faint, stellar companion sitting almost directly in its glare. This is, in Montargis' own description, that's the conclusion of a search that has effectively run for a century, ever since astronomers first noticed the strange, repeating 2,100-day rhythm in the star's brightness and started arguing about what could possibly be causing it. And here's the part that matters for anyone who saw a version of this story online in the past few days. Credited to the wrong telescope, this image did not come from the James Webb Space Telescope. Webb is extraordinary at what it does, peering through cosmic dust and infrared light, capturing the early universe, resolving faint, distant galaxies. But the picture actually responsible for this discovery came from a ground-based observatory in the Chilean desert, using an instrument purpose-built for exactly this kind of needle in a lighthouse beam imaging. What most people sharing that viral image are not seeing is that they've credited the wrong eye for one of the more elegant technical achievements in recent stellar astronomy. The confusion is easy to understand, even if it's wrong. James Webb dominates space telescope headlines for good reason. Nearly every major astronomical announcement of the last few years has carried its name, so when a striking new image of a famous star starts circulating, plenty of people assume Webb by default before checking the actual source. According to the researchers' own account of the work, this detection specifically required the combination of ground-based extreme adaptive optics and a coronagraph tuned to suppress exactly the kind of overwhelming nearby glare that Betelgeuse produces, a use case that plays directly to the VLT and SPHERE's specific strengths, developed over years for hunting faint objects hiding next to bright stars. Webb, brilliant as it is, was simply never the instrument built for this particular needle in a lighthouse problem. Coverage of the discovery has already spread through major outlets and observatories crediting ESO correctly, but the misattributed version, the one naming Webb, is still the one racking up shares, which tells you something honest about how discoveries actually travel online. Accuracy rarely wins the race against a more famous name. There's an exact date on the calendar that matters for the next chapter of this story, and it isn't a guess. Also under construction in Chile, on a mountaintop not far from where the VLT already stands, is the European Southern Observatory's extremely large telescope. A single mirror nearly 40 meters across, built from almost 800 individual segments, designed to gather more light than every other large optical telescope on the planet combined. According to ESO's own updated construction schedule, the ELT is set to achieve telescope first light in March 2029, followed by full scientific first light in December 2030. When that happens, astronomers will have an instrument roughly 15 times sharper than the Hubble Space Telescope, pointed at exactly the kind of target Betelgeuse represents. Close, bright, and until now, just barely beyond the reach of direct imaging. Researchers on the Betelgeuse companion team have already said, in describing their long-term hopes for the project, that an instrument with that level of resolving power should be able to image Betelgeuse's own surface and any orbiting companion in a level of detail no current telescope can match. That date, December 2030, isn't a hope. It's already on the construction calendar, mirror segment by mirror segment. Now, the honest part, because this story isn't fully closed yet, and pretending otherwise would be dishonest. The research team itself is careful about the word they use, candidate. The faint point of light captured beside Betelgeuse matches everything the century of brightness data predicted. The right position, the right separation, the right timing to explain the 12,100-day rhythm. But a single image, however clean, is not the same as an independently confirmed orbit measured over multiple observations. There remain two live possibilities scientists are still working through. One is that this is exactly what it appears to be, a genuine, gravitationally bound companion star finally caught on camera after 100 years of failed attempts. The other, less likely but not yet fully ruled out, is that the detection could reflect some other structure in Betelgeuse's complicated, dusty surroundings, the same kind of stellar environment that produced the Great Dimming's dust cloud in the first place, mimicking a point source in a way that further observations will need to rule out. Montargis and his team have said openly that a key open question is what a real companion of this kind would mean for how Betelgeuse evolves toward its eventual supernova, whether an orbiting star could actually influence the timing or nature of that explosion. That question is, as of this discovery, genuinely unresolved. Confirming an actual orbit, measuring the companion's position relative to Betelgeuse over multiple future observations, and in watching it trace out a predictable path consistent with gravity rather than staying fixed like a background object or a static structure, is the specific next step the research team has flagged as necessary before anyone can call this fully settled. Until that follow-up data comes in, candidate companion is the honest, accurate description, and confirmed companion is not yet earned, however strong the circumstantial case already looks. Step back from Betelgeuse specifically. And there's a larger pattern worth noticing here, one that shows up again and again across the history of astronomy. This wasn't a story about a sudden freak discovery. It was a century-long argument between a persistent pattern in the data and the technological limits of the era trying to explain it. The 12,100-day signal was sitting in brightness records that astronomers 100 years ago could already see. What nobody had, until 2026, was an instrument capable of suppressing enough starlight to actually resolve the cause. That's the quiet, unglamorous engine behind most real progress in this field. Not a single genius insight, but the slow, decades-long process of building tools sharp enough to finally answer questions the evidence had been asking for a lifetime. What most people are not seeing when a headline like this goes viral is how much waiting sits underneath it. Waiting for adaptive optics good enough, for a coronagraph precise enough, for a team patient enough to keep pointing an expensive telescope at the same stubborn puzzle year after year. Confident that the physics underneath the data was real even when the picture kept coming back empty. Betelgeuse itself embodies the same lesson on a cosmic timescale. It is a star finishing a multi-million-year life story whose final chapter, the supernova, could arrive tomorrow or in another 100,000 years, and either way, a relatively tiny span of existence, watching, measuring, and arguing about the details right up until the moment the light finally changes for good. There's also something worth noticing about power here. Not political power, but the quieter kind. The power to simply resolve what was previously unresolvable. For 100 years, the answer to whether Betelgeuse had a companion depended entirely on whoever controlled the sharpest available optics and the patience to keep pointing them at the same tired question. That's the actual currency of observational astronomy, and it rarely gets discussed outside the field itself. Not brilliance alone, but access to bigger mirrors, better adaptive optics, more telescope time, and the institutional patience to fund a search that might, and for 100 years did, come back empty. The 2026 image didn't happen because someone suddenly got smarter about Betelgeuse. It happened because the tools finally caught up to a question that had been sitting there, fully formed, since before anyone alive today was born. There's something worth sitting with in the fact that Betelgeuse has likely never been alone. For as long as humans have looked up and traced the shape of a hunter in the winter sky, the bright orange shoulder star they were looking at may have had a quiet companion tucked just inside its glare the entire time, present in every ancient sky watcher's gaze, in every medieval star catalog, in Orion's belt legends told around fires long before telescopes existed. Ours and invisible through every single one of those centuries, because the only eyes available were never sharp enough to separate 2 points of light standing that close together. It took a mirror built and polished on a mountaintop in the Atacama Desert, and an optical trick designed specifically to defeat the glare of a star too bright for its own secrets, to finally see what may have been sitting there the entire time. Somewhere in that gap between what has always been true and what we only just learned how to see is most of the actual history of astronomy. Picture the two of them out there right now, however this ultimately gets confirmed. One enormous, dying, swollen star, nearing the end of a life measured in millions of years, and one small, faint, patient point of light that has apparently been orbiting alongside it long enough to leave fingerprints in 100 years of brightness records without ever once being seen directly, until a specific night, on a specific mountain, when a specific combination of mirrors and masks finally let a little of that faint light through. Whatever it turns out to be, it waited a very long time to be found. So here's everything in one breath. Betelgeuse is a dying red supergiant on Orion's shoulder, roughly 550 light-years away, whose brightness has puzzled astronomers with an unexplained 2,100-day rhythm for over a century. Its 2019-2020 great dimming briefly sparked supernova fears, before ESO's Very Large Telescope revealed it was really a self-made dust cloud. Decades of failed attempts to directly image a suspected hidden companion finally succeeded in 2026. When the VLT's Sphere instrument captured the clearest image yet of a candidate companion star, nicknamed Betelgeuse B, not, despite what's spreading online right now, an image from James Webb. Whether it's a confirmed companion or something else entirely in Betelgeuse's dusty surroundings is still being worked out, and the extremely large telescope, due for full scientific operation in December 2030, is expected to help settle it for good. If you want to be here when that confirmation actually lands, or when Betelgeuse finally does what every red supergiant eventually does, subscribe and turn on notifications, because I'll be covering it the moment real data comes in, not before. One question before you go. If you had to bet, is that faint point of light next to Betelgeuse a genuine companion star, or something stranger still hiding in the dust? Tell me in the comments. I read every single one.